Okay guys, in this video we're going to look at our second example using the law of cosines, or at least a situation in which the law of sines wouldn't be available to us. And so this particular case is the side case, or the instance where we would actually know all three sides of our triangle, but we wouldn't know any of the angles. And so in order to solve this, really what we need to be looking for is missing angles. And so I'm going to go ahead and set this up here. And as a matter of fact, what I suppose mean by set this up is we're going to look at what we know and what we don't know. So let's start with this. We know that lowercase y would be 25, lowercase x would be 23, and lowercase z here would be our 26. So we're going to say x equals 23, y equals 25 units in length, and z is equal to 26 units in length. So across from this, as we normally do, we're going to write measure of angle x, the measure of angle y, and the measure of angle z, and go search for these. Now in terms of the side case, we certainly can see here that we have no side angle pairs. The question really becomes a lot of time, well, what angle should I solve for first? And so in terms of solving for angles, when it comes to solving triangles, we're going to write a little phrase here. Determining which angle to solve for first. Go big or go home. So you just remember this little phrase right here, go big or go home. And I suppose what we mean is, in terms of which angle I would solve for first, I'm going to look for the biggest one. Because in certain possible instances, we're going to see that it's not possible, and we'll always be able to determine that just by looking at solving for the biggest angle first. So now, in this particular case, we're going to look for the biggest angle, which in this case would have to be this measure of angle z right here. And so in terms of, well, which of our formulas would I use here? Because this isn't a's, b's, and c's, this is x's, y's, and z's. Well, what you got to understand is that these formulas look the same way. So in terms of how these formulas look, remember that if we're looking for angle z, then our formula is going to end in angle z here. And so whatever angle we ended our formula with, this was the same as the side we started with. Well, I know then that my formula that I'm going to use has to start with lowercase z. And so we'd say z squared. Well, what would that equal? Well, it's Pythagorean looking, so we'd have x squared plus y squared. And so in terms of our cosines formula, law of cosines, we'd always say minus 2 times the product of these exact two sides, and then this is always going to be taken times the cosine of the angle that is the same as the side length we're starting with. So in terms of what we know, well, we know z, we know x, and we know y, we know this x and we know this y. The only thing we don't know is going to be this capital Z right here. And so what we want to do is this. We're going to go plug in everything we know, and then we're going to get by itself the one thing we don't know. And so using law of cosines here, we're going to have to leave this cosine of capital Z, but everything else we know we'll put in the right spots. And so we say 26 is my Z. Well, then I'm going to have 23 here and 25 for x and y respectively here. And so these are 23 and 25. Well, then these are 23 and 25. So in order to solve for Z here, we need to, first of all, let's make sure we write a note. We are going to, 1, simplify both sides, 2, isolate the trig function, and then use inverse trig functions to find the angle. Okay, so in terms of simplifying both sides, the only thing I can actually give you a recommendation to do is take your time. So for instance here, 26 squared, I would actually take my time. I would say 26 squared is 676. So on the left here we have 676. This is equal to 23 squared plus 25 squared. As a matter of fact, 23 squared plus 25 squared, I actually go ahead and do that calculation right now. We get 1154. So with these two together, I get 1154. And this is now minus 2 times 23 times 25. We actually need to do that here. We say 2 times 23 times 25. What we end up with is this. We get 1150 here. So the one thing I want you to write here is 1150 cosine of z. We want to be very, very careful here. We're going to get the cosine of z by itself. So the way we do this is we're going to have to, first of all, subtract our constant off of the right-hand side. One thing to keep in mind is this. We cannot take 1154 minus 1150 cosine z and say that it's 4 cosine of z, because these both don't both have a cosine of z on them. So they're not like terms. And so we got to get rid of this constant first, And when we do this, I suppose we get 676, okay, minus 1154, 1154. And so we get negative 478 on the left, and this is equal to, over here, it would be negative 1150 cosine of z. So to finish this off, again, we need to isolate the cosine of z. So we're going to divide both sides by negative 1150. And what we get on the left side here is positive 478 over positive 1150. Now, normally we could reduce that, but because what it is that I'm interested in doing is solving for z, we don't necessarily have to do that. What we're going to do is we're going to use an inverse trig function to undo the cosine here. So to undo cosine, we'll do a cosine inverse of both sides, cosine inverse function, and what we'll put in over here is the left side, 478 over 1150, and what we'll put over here is the cosine of z. So neat, the cosine and cosine inverse cancel, and so we get z is actually exactly equal to the cosine inverse of 478 over 1150. But let's go ahead and solve for this here. That's exactly our answer. Well, let's get an approximate value. We're going to do cosine inverse of 478 divided by 1150, and we get about 65.4 degrees. So I'm going to write 65.4-ish degrees. Certainly I'll put a box around this. I also want to go up here and write this as 65.4 degrees. Also on my picture, 65.4 degrees. So now the neat thing about this is, if we're solving for this, we certainly need to go back and find the x and y's angles as well. But look what we have now. We have a side angle pair. So in terms of which one I'll solve for first, looks like y would have to be the bigger angle, being across from the longer side. So let's go ahead and set ourselves up here using the law of sines. We get the sine of capital Y, which we don't know, over the length of its side opposite, 25, would be equal to, now we'll use our side angle pair here, the sine of 65.4 degrees over 26, which is the length of its side opposite. So using our cross product here, we would get 26 times the sine of capital Y is equal to 25 times the sine of 65.4 degrees, and we could divide now both sides by 26 to get our trig function by itself. So the sine of this angle is equal to 25 times the sine of 65.4 degrees all over 26. And so what we're going to do now to undo our sine is we'll take a sine inverse of both sides. So we get y is exactly equal to the sine inverse of 25 sine of 65.4 degrees all over 26. And we'll get this on a calculator. Let's find the inner portion first. I suppose what I mean by that is what we're about to take the sine inverse of. We'll do inside here, clear all this out, in parentheses 25 times the sine of 65.4 degrees, two end parentheses, but I'm going to divide this by 26. So our inner decimal here is about that, and we're going to do the sine inverse of our answer, and that gives us about a 60.95 degree angle, or about a 61.0. So 61.0 degrees. We'll go put this up here for angle y, 61.0 degrees. We'll go put this on our picture, 61.0 degrees. And the thing to keep in mind here is, now that we know those two angles, okay, we can solve for the third just by using addition and subtraction. So 61.0, or 61, plus 65.4, we'll take that away from 180, or take 180 away from it, and what we get is about a 53.6 degree angle. So 53.6 degrees. We'll go put this on the picture here, and we have our triangle solved. So that's an example of our side case in which we had different letters that was good to look at, but also where we have to solve for the angle. So isolate the trig function, and we'll use inverse trig functions to undo it and solve for our angle. Cheers.